Math and Beats. This is a video in which we're going to look at a variety of examples involving antiderivatives. Let's take a look at these examples. First, we'll start by looking at a couple of indefinite integrals. And so let's find each of the following indefinite integrals. First one. Now at first this looks a little daunting, but we're going to dissect it piece by piece. And that is, here we go. The indefinite integral of this crazy sum, the negative cotangent of x times the cosecant of x divided by 2, plus the quotient x to the 3/2 plus the 5th root of x to the 4th all divided by x to the 6th, minus 5 divided by the square root of 1 minus x squared, plus pi minus 3 to the x. So the first thing we want to take note is we can definitely use the constant multiplier rule within this indefinite integral, and we can split it up into 5 different indefinite integrals for which we use the sum and difference rules. And so we're going to do that. However, there's this one term right here I'm going to circle. Now, that term is a sum in the numerator and just a single term in the denominator. Now, as of right now, when we have gone through the progress of the videos and prior to this video, we have no discussion of some backwards quotient rule. And so instead, we have to figure out a way to manipulate that. Notice that this quotient term here is really the same as x to the 3/2 divided by x to the 6th plus an x to the 4/5 divided by x to the 6th. So we could split it up into 2 different terms. And hence, this is the same as the integral of negative 1/2 times the cotangent of x times the cosecant of x with respect to x. And then we have a plus an integral of x to the 3/2 over x to the 6th with respect to x, plus an integral of x to the 4/5 over x to the 6th with respect to x, minus, I'll just pull that 5 out in front, 5 times the integral of 1 over root 1 minus x squared with respect to x, plus an integral of just pi dx, and finally minus an integral of 3 to the x with respect to x. So really we split this up into now 6 different indefinite integrals using the sum and difference rules, and we can go integral by integral, if you will, and find out what we get. All right, the first indefinite integral, notice that negative cotangent x times cosecant x is the derivative of the cosecant of x function times that half out in front. So that first one's going to be a 1/2 cosecant of x. And then for that second one, I'm just going to simplify x to the 3/2 divided by x to the 6th into a single power of x so that we can use our power rule. So this will be plus an integral 3/2 minus a 6 is an x to the negative 9/2 power. Integrate that with respect to x. And then plus, we'll do the same thing for that third integral. Simplify that quotient of powers of x. X to the 4/5 divided by x to the 6th is an x to the negative 26/5 power. Integrate that with respect to x. And then for this fourth integral right here, we have some options. We see the 1 divided by square root 1 minus x squared. The antiderivative of that function is the arc sign, but since there's a negative in front, we could technically use an arc cosine as well. So it's kind of up to us what we want to do. I'll go ahead and use the arc cosine just for fun and write this as a plus a 5 inverse cosine function. The plus being there because the derivative of the arc cosine function is a minus 1 divided by square root 1 minus x squared. And then we have that plus the integral of pi dx, well, derivative of something that gives a constant is just a linear function, so that's going to be a plus a pi times x. And then finally, minus, using our general exponential rule, gives us a 3 to the x divided by natural log of 3. And let's go ahead and just write our constant out there while we're at it. So then, last piece, we have to integrate both of these, and we get a 1/2 cosecant of x, and then power rule, so plus an x to the negative 9/2 plus a 1 divided by negative 9/2 plus 1 plus an x to the negative 26/5 over, or excuse me, negative 26/5 plus 1 divided by negative 26/5 plus another 1, and then plus that 5 arc cosine of x plus that pi x minus a 3 to the x divided by the natural log of 3 plus a constant. So simplifying even further gives a 1/2 cosecant of x, and then notice that right here negative 9/2 plus 1 is a negative 7/2. So that power is going to be a negative 7/2, and then we're dividing by negative 7/2, which is the same as multiplying by a negative 2/7. So this would be a minus 2/7 x to the negative 7/2. And then similar for this piece, negative 26/5 plus 1 is the same as negative 21/5. So I'm going to have that as my power, and I'm dividing by that, which is the same as multiplying by a negative 5 over 21. So minus a 5 over 21 x to the negative 21/5 power plus a 5 arc cosine of x plus a pi x minus a 3 to the x divided by the natural log of 3 plus a constant. And there you go. Here is the general family of curves, such that when differentiating them gives the original integrand in our indefinite integral. So just dissect it. If you have a lot of stuff going on, go term by term and integrate term by term. If you have something like right up there that we need to simplify further and split the terms up, then we do that as necessary. So there's an initial example of an indefinite integral involving a variety of different things. Here's another indefinite integral. This time we got a whole bunch of different variables going on. In this integral, we have the indefinite integral of 6w minus q squared y plus an xw squared with respect to w. So part of the intent of looking at an integral like this is to remember that the differential here, dw, tells us to treat the variable w as the variable of integration, right? So in other words, this is saying w is our independent variable in this case, and that means all other variables that we see are treated as constants. So that would tell us that q, y, and x are all constants in this situation. And thus, I can integrate term by term here. So let's just write it. This is the integral of 6w with respect to w minus the integral of q squared y with respect to w plus the integral of xw squared with respect to w. The very first integral of 6w with respect to w, all there is w's in there for variables. So it's a simple power rule. That is going to be a 3w squared. The second one, the minus integral of q squared y with respect to w, has no w. So you're basically integrating a constant in that situation. Since q and y are both constants, hence q squared times y is also some constant. So I'm going to get a minus q squared y times w. And finally, that last integral, xw squared with respect to w, well, w is the variable here, right? X is a constant. So applying the power rule on the w squared is going to give us a plus a 1/3 x w cubed, and then plus that constant. So that example is supposed to help us remember that the variable of integration in that differential, very important, right? Tells us with what variable we treat as the independent variable. So let's go ahead and take a look at one more example here in this video, and that is right here. Let's suppose that a ball is thrown upward, assume we're on planet Earth, with an initial velocity of 5 meters per second. The ball is thrown from the roof of a house, which is 6 meters above the ground. All right, so you just go on the top of the roof, throw a ball up in the air, and see what happens. First part of this problem is using antiderivatives. Let's find formulas for the velocity and position functions of the ball at time t, assuming bigger than or equal to 0. All right, so in this situation, there is a way to find the formulas if we just know the general formula, but the point of this is to see how we can use the antiderivatives to come up with this. All right, so in order to do this, we have to know something, and that is that the acceleration on an object on planet Earth is constant. In this case, we're using the metric units of meters and seconds, so it is negative 9.8 meters per square second, at least approximately. So that is something we need to know, because the acceleration on the ball is constant. And so this, of course, is the same as the derivative of the velocity function at time t. And so what that allows us to do is come up with the velocity function by integrating our acceleration function. Since, of course, the acceleration function is the derivative of the velocity function. And when we do this, well, of course, we're just integrating the constant negative 9.8 with respect to t here. And when we do that, we get a negative 9.8 t and then plus some constant. And so this constant we need to find. And because in this problem, we have some other information given to us. So remember up here, it says the initial velocity of this ball being thrown is 5 meters per second. So we can use that. We can use the fact that at time 0, the velocity is equal to 5 meters per second. And so if I plug in 0 into my general family of possible curves here, I'm going to get negative 9.8 times 0 plus that constant, telling me that that constant in this particular case has to be equal to 5. So this is a situation in which, given some information about the particular curve that we're finding that's an antiderivative, if we know a special point on that curve, it allows us to specify exactly the one and only one curve out of all of the infinitely many different antiderivatives that are possible that this must be. And hence, we get that the velocity function here has to be negative 9.8t plus a 5. So there's the first part. We found our velocity function. The second part is we are asked to find the position function. Let's call the position function s of t here. Well, similarly, because v of t, right, is the derivative of the position, then it follows that s of t must be found by integrating the velocity function. And to do that, we integrate the boxed in result that we found just a moment ago, negative 9.8 over 2 t squared using our power rule, plus a 5 times t, and then plus some other constant, let's just call it d for the time being, which simplifies to negative 4.9 t squared plus 5t plus d. And similar to how we knew the initial velocity for finding that constant in the previous part, go back here, right there, we knew that the initial position of this ball was at 6 meters above the ground. And so in this case, S of t is going to be able to be simplified in that finding d by knowing that S of 0 is 6. And so if I plug in 0 into my result I just found, negative 4.9 times 0 squared plus a 5 times 0 plus d, it tells me that that value of d has to be 6. And thus we get S of t here is a negative 4.9 t squared plus a 5t plus a 6. So you can see that antiderivatives are useful in various situations. There's so many you could talk about, but we're just getting introduced here. Second question, kind of a random question. What is the maximum height above the ball, above the ground? Well, in this situation, we know our velocity function, which is the derivative of the position function, is given by negative 9.8 t plus 5. And so because my position function is a quadratic function, I can figure out when its derivative is equal to 0, and we know at that point will be the vertex of this function. So I just set my derivative equal to 0, and when doing so, this gives that t must be equal to 5 divided by 9.8, which, if you press some buttons, is approximately 0.5 seconds, approximately. So it's going to occur at 0.5 seconds approximately, but we're being asked what the maximum height of the ball actually is, so we need to put that value of t back into the position function. So S of 5 divided by 9.8 is going to be approximately 7.27 meters above the ground. So you can plug it in and verify that that's the numerical value approximately. Finally, we are asked, how fast is the ball moving when it hits the ground? Well, we first need to know when the ball actually hits the ground. We know that S of t, we already found, was negative 4.9 t squared plus a 5t plus a 6. And so to figure out when the ball hits the ground, it's the same as figuring out when that value of S is equal to 0. Using the quadratic formula, t is going to be equal to negative 5 plus or minus square root of negative 4.9 squared minus a 4 times a negative 4.9 times a 6, all divided by 2 times a negative 4.9. And so you get two different values there when you press some buttons, and one of them is negative and one of them is positive. So the one that we care about is positive because that's after we have thrown the ball, and this is approximately 1.72 seconds after the ball has been thrown. So now what we must do is take this value of t and actually plug it into our velocity function, since we're being asked how fast is the ball actually moving when it hits the ground. So remember, v of t from right up here, right, was negative 9.8 t plus a 5. So we're going to plug that in. Let me just rewrite it. V of t is negative 9.8 t plus 5, and therefore my velocity at this instant of approximately 1.72 seconds is going to be negative 9.8 times 1.72 plus 5, right? A little bit of round out there here. And if you press some buttons, you'll get that this is approximately negative 11.94 in terms of meters per second. So that negative sign attached, of course, is indicating that the ball is moving downwards when it hits the ground. However, we are specifically asked to find how fast the ball is moving when the ball hits the ground, and therefore we want the absolute value of this, giving us that the speed at this instant is going to be equal to, again, approximately 11.94 meters per second. So the ball hits the ground approximately 1.72 seconds after it has been thrown, and when it hits the ground, it is moving at a rate of 11.94 meters per second. And there you have it. So that is it for this video. We looked at a couple of indefinite integrals, one which had a lot of different things happening in it, and also another indefinite integral that helped us remember that it is important to pay attention to the differential variable within the integral, so we know with what variable we treat as the independent one. And then here's a little application that we just looked at using indefinite integrals to help us find other functions, in this case velocity and position functions. Moreover, this last example is important because given some specific point on one of the curves that belongs to the general family of antiderivatives, then that allows us to specifically find that value of the constant when integrating that narrows it down to the exact curve for which we want in that situation. But that is it. That is the end of this video. It is Math and Beats. I'm out now.